Yeah, welcome to the higher maths wave function topic for solving equations. And what we're going to look at today is using what we already know about using the wave function or converting using the wave function to solve trigonometric equations. And just like the last video, this is two skills we already know how to do. Okay, we already know how to use the wave function to convert it into a single trig function, and we already know how to solve trig equations. So this is going to be nice and easy. Okay, just same again, get this in your notes. Part 1A is just writing it in the wave function. I've already got that there for you. By all means, give it a wee try. I'm going to go over part B now though. Okay, so give it a wee try first. I'll just go down in a wee second. Okay, so there you go. That's what we should have. 5 cos x plus sin x equal to root 26 x minus 11.3. Okay, now in part B, hence solve the equation where that same wave function is equal to 2. Okay, so for part B, we're solving where 5 cos x plus sin x is equal to 2. Okay, now hence, just same as every question, hence just means right, use what you've just done. So what we've just done is we changed this into root 26 cos of x minus 11.3, and that's equal to 2. Okay, now to solve this, just the same as we solved earlier, we only got one term, one trig term, so we're just going to get everything to our side. Okay, we're going to cancel out that root 26 by dividing by root 26, so it's 2 over root 26, and then we're going to deal with the cosine. Okay, we're talking about cos, we're talking about a positive, so we're talking about the first quadrant and fourth quadrant, and we do the inverse cos of 2 over root 26. Maybe seconds on it. 2 over root 26, which is 66.9 degrees. Okay, so my two solutions for this is x minus 11.3 degree is equal to 66.9 and 293.1, which means x, when you add on the 11.3, is 78.2 degrees. Yep, that's fine. And 304.4 degrees. Okay, so that's us solved. Now that's what I mean, there's no new knowledge here. We know how to do part A already, so much so that we don't even need to kind of have instruction for that, we shouldn't need that. And part B is just what we learned earlier on in the course. Okay, so just putting two things together. Now, that's a third way to solve trig equations, putting it into the wave function and then just solving as normal. For the vast majority of exam questions I've seen, they've done it in two parts like I've got here. Now, let's look at one just to finish off this topic, where it doesn't do that, it just gives you in one simple question. Now, what we should be looking for here, if it's a single trig function, we solve it like we did at the bottom here, just cancel everything out and then deal with it. These ones here, most of the time, or all the time up until now, we've always had a sine 2x and a cos 2x here. And that meant we were subbing in one of our expressions, and then we were simplifying, factorising, and solving. Okay, but here we don't have a double angle, and that's the real key for when we use this. Okay, for when we use these wave functions to solve. Okay, so this one here, we're solving a trig equation that's got a sine x and a cos x. They're both the same value in the trig, so it's single x there, single x here. So we need to use the wave function. Now what it doesn't do here is it doesn't tell us what wave function, whether it's k cos x minus alpha or k sine x minus alpha or whatever. But what I would do is I'd try to pick one that matches up nicely. Okay, now because the cos expansions keeps cos with cos and sine with sine, I'm going to use that. And because there's a negative in the middle here, well actually it doesn't really matter because it's a negative cos. So I would just use either one of those cos ones. I'd maybe do cos x plus alpha. Okay, it doesn't matter which one you do. It's not going to matter, but I'm going to use k cos x plus alpha. Okay, and I'm going to pause it now and just do the wave function with k cos x plus alpha. You can give it a try as well. Okay, back in a second. Actually, no, I'm not. Now, I've changed my mind with this, and I'm going to show you why. What I'm going to use instead is k sine of x minus alpha. Okay, and the reason for that is, if possible, I want to keep my wave function in the first quadrant, which is what happens when both of my equivalencies are positive. Now, because we've got a negative cos x there, the only one that has a negative cos x is k sine x minus alpha. If I chose k cos x plus alpha, it didn't have that. So it would have made the equation solving a little bit trickier. Now that's maybe a wee mistake I've made, apologies for that, but I hope this quick explanation covers it up. So sine x is there and sine x is there. Okay, cos x is here and cos x is here. Okay, so looking at equivalencies, sine x matches up to sine x, so k cos alpha is equal to 3, and then negative k sine alpha is equal to negative 1. So k sine alpha is equal just to 1. Okay, and that's what I mean. I've changed my mind to use this one so I keep both of these positive, so that over here when I do my cast diagram for my tan, I'm working in that first quadrant, and I'm thinking that just makes my solving the equation that I'm about to do after a little bit more straightforward. Okay, apologies for that. Give me a wee second till I finish this off. Okay, so that's it done there. And just to emphasise again, it wouldn't matter what one you picked. You could have picked either one of the four and the equation's still going to solve itself and your wave function is still going to be correct. We saw right at the start, right in the very first video, that it could be any of sine and cos there. The equation that we get when we do 3 sine x, or the graph we get when we do 3 sine x minus cos x, can be interpreted as either a sine or a cos graph moved either way. So don't worry too much about it. And what we're doing here is just dealing with that left-hand side. So we've got a single trig equation to solve the equation. Okay, so what we're solving now is actually the equation we're given to solve. Excuse me, sorry, get my sick. The equation we're given to solve is, let's call it an imaginary part B, is 3 sine x minus cos x is equal to 1. Okay, but now because we've changed this over, we can use that root 10 sine of x minus 18.4, so that's a bit messy, equal to 1. To make it a lot easier to solve, we've got a single trig function now, so we just cancel things out to leave the x by itself. 1 over root 10. We're dealing with sine, we're dealing with a positive, which is good, so we're dealing with a and s. Inverse sine of 1 over root 10 is 18.4. Okay, so inverse sine of 1 over root 10 is 18.4. This is the same as what we've just got, but that's just a little quirk of the triangles, right angle triangles, and the tan and cos function in there. Okay, so x minus 18.4 is equal to 18.4 in that first quadrant and 161.6 in the second quadrant. Okay, and then we're just adding on 18.4 to both, so that'll be 36.8 degrees and 180 degrees for our final solutions. Okay, so sorry that was a little bit rambling maybe in that one, but I'm hoping you can see new kind of situation where you've got a single sine x cos x, you need to convert using the wave function into a single trig function and then just solve it as you have done before. Okay, now most of the time they'll give you what to use in the part A. If they don't, you can choose any one you like. If possible, choose it so both of these things are positive and then just solve straightforward as again. Okay, thanks for bearing with me there. Any issues, get some help in class, come and ask your teacher, come and ask me, whatever it takes. Cheers, bye.